Hello everyone, you are welcome to the Chemistry, Biology and Math Revision channel. Here we discuss about chemistry, biology and math through past papers as well as some topic-based revision. So the first paper we're introducing today is the Pearson Edexcel International A-Level Chemistry for January 2021, Unit 6. This paper is 50 marks, so let's go straight to the first question. A student carries out some tests on 4 aqueous solutions. They are solutions A, B, C, and D. It's usually important when you're reading to try and underline some important things that could help you when you're trying to answer the question a little bit later. So here we can see they say these are aqueous solutions A, B, C, and D. One of the solutions is aqueous barium chloride. So they've given us barium chloride, the identity, but they've not told us if it's A, B, C, or D. The student is asked to add A to samples B, C, and D in separate test tubes, a small amount at a time until there is no further change. The container is a solution of a solution A has a hazard label, which is basically this one. Identify the hazard indicated on this label. This means corrosive. Yep, it means corrosive. That's very easy to identify actually. It's very unique. Describe how you would add small amounts of A until there is no further change, and name the apparatus you would use. So the key thing here they've told us A is one of the 4 solutions we have, so it means it's going to be a liquid, and we need to add it little by little. So it means we need to get some apparatus that has the ability to add a little amount at a time. And the burette can be very perfect, or a pipette with this ability can also be a good one. So we will add drop by drop because it's a liquid, and then you can use a pipette or a burette. I would recommend a burette because it's better at adding drop by drop than a pipette, because a pipette you need to be okay, or you need to have experience controlling it to release a drop by drop, but a burette is easy to use. Let's get to the next part of this question. Part B1. B is a blue solution. Now, every time they talk about a blue solution, please remember to think about copper in oxidation state +2. When A is added, so B is a blue solution. So they say when A is added to B, the mixture forms a green and gradually to yellow. Now here, this is very important. However, if you do not know this yet, we can practice together. The blue solution is usually going to be hexa aqua copper 2. Now, if you see a blue turn through green and then finally to yellow, it means something was added to the blue solution, and that thing must have been concentrated hydrochloric acid, because the concentrated hydrochloric acid will interact with the blue solution going through a ligand substitution reaction. Ligand substitution. So actually, the real reaction can be as below: copper H2O 6 with 2 plus, and then plus 4 HCl, giving us CuCl4. This is going to be 2 minus plus the 6 water ligands that have been replaced basically. So the appearance of the blue color is going to be due to this, and the yellow is going to be due to this. The green is going to be due to the mixture of those two. So it means there will be some product being formed, which is yellow, as well as some reactant still being left behind, which is going to be, of course, the copper, hexa aqua copper 2. So that creates the green. So this information here is giving you is basically giving you the identity of B as well as the identity of A. So we can be able to tell one is hydrochloric acid and one could be hexa aqua copper 2 plus. So they told us to give the formula of the cation in B. We know because B was a blue solution and it formed a yellow when you added a specific solution B. That is no other way except knowing that A was copper 2. This is going to be best. That is the cation, because here you may not know, but it's usually going to be, of course, copper 2, which is in aqueous solution is going to be like that due to the ligand surrounding it. So part 2 says when A is added to C, vigorous effervescence. Vigorous effervescence, that means maybe something is there is a reaction between an acid as well as maybe acid-alkali acid-base reaction. So effervescence occurs as the gas produced. I'm going to remove this because it was to do with the other part. So let me remove it because we no longer need it. So here they say occurs and the gas produced turns lime water milky. This gas that turns lime water milky is going to be carbon dioxide. They say identify by name or formula the gas produced as CO2, which is easy. Suggest the identity by name or formula of the cation in C. Now remember, we have already identified that B is a copper 2 plus, and A, like I told you here, could be concentrated HCl. Again, we see here A which could be concentrated HCl being added to C, and effervescence occurs. It tells us that A could be an acid, and because you've reacted an acid with something to produce carbon dioxide, that C could have a carbonate, as you see here. Then next they say, identify A by name or formula and justify your answer. So I can confidently say that A was concentrated hydrochloric acid because it forms a yellow color of tetrachlorocuprate when it reacts with that. And you could go on to say, and also it causes effervescence of a gas that turns like water milky when it's reacted with something suspected to have a carbonate ion in it. Next part, when A, which we are predicting to be HCl, is added to D, which we do not know, no change is seen. It means here we have no carbonate. So it could be something else, and that could be maybe it's a sulfate. It could be anything that cannot basically react with acid to release, of course, carbon dioxide. So here there's a small amount of this mixture is added to B, and a white precipitate forms. So we know, you remember, they say a small amount of this is added to B and a white precipitate forms. So they say, suggest what can be deduced about B and D. We know B contains a sulfate because basically it did not form, when HCl was added to it, it did not release a gas. And we also know, since we know this one has a sulfate and they've told us one of the 4 solutions was barium chloride, it leaves D alone as the unidentified one, so therefore B should be barium chloride. So let's go to the next part. They say a concentrated solution of ammonia is added to B. Remember, B is already hexa-aqua copper 2 plus. Initially a pale blue precipitate. If a pale blue precipitate forms when this ammonia is added, that is a deprotonation reaction. Remember, when one of the hydrogens from one of the water ligands is being taken away. When more ammonia is added, this means more ammonia addition is excess. And you guys know when copper reacts with ammonia in excess, it forms a deep blue solution. So they say the precipitate dissolves, forming a dark blue solution. This is again a giveaway. It means we have replaced the deprotonation reaction has now become a ligand substitution reaction. So identify by name or formula the pale blue precipitate and the species responsible for the dark blue solution. So the pale blue precipitate formed in between could be this one here. Again, could be this one here. When we have CH2H2O, 6, 2 plus, when it reacts with ammonia, because this is 2 plus, I'm going to put 2 ammonias here in the first deprotonation, so we will get copper, H2O, 4, and then let me clear here, OH, 2. These are the ones that have lost one of their hydrogen. Each has lost 1 hydrogen to the ammonia. Now this one here, I can put concentration brackets, but it's a solid because it's neutral. And then plus, the other side we're going to have ammonium, but they're going to be 2 because each of the ammonia has gained an extra proton to form the ammonium. So this is what we are looking at when the deprotonation reaction occurs. However, when further deprotonation or ligand substitution occurs, these 2 water molecules are going to go away and those OHs are going to go away. So we form something like that as the final complex in here. So let's do the final part of question 1. A solution of the sodium salt of EDTA, this one here, is added to the sample of solution F. The solution turns pale blue. They say write an equation for the reaction of this. When this occurs, actually, we are causing an increase in entropy. So here we can see this part here when it reacts with EDTA. Remember, EDTA is a hexadetent ligand. It means we just need 1 ligand to form the octahedral complex, basically. So it's going to be EDTA in here. Remember, each of the EDTAs, the EDTA basically has 6 negative ions because it comes out, in this case, it comes out 4 minus, 4 minus. So it means we are going to have a balance of 2 and 4 minus, which is going to be a -2. So we will form This one here comes and kicks out all of these because it's a hexadetent. However, due to the negative 4 charges, they are going to neutralize 2 of these, leaving a -2 on the outside, and therefore we will have this kind of equation going on. The ammonias that are inside here are going to be released out, and the 2 water ligands are going to be released out as water molecules. This brings us to the end of question 1, so we'll go straight to question 2. Question 2, the students were taught to determine the concentration of a solution of potassium chloride 5. 2 methods were used, precipitation and titration. So the first one we see, they say bubble excess sulfur dioxide into 100 centimeters cubed of potassium chloride 5 solution. Then you boil the resulting mixture to remove the excess SO2. Now you have to know this SO2 is actually toxic, so when you're carrying out this experiment, you have to use a fume cupboard. And then add silver nitrate solution until no more silver chloride precipitate form. This is again using the precipitation reaction to determine the concentration of potassium chloride. So here we're going to be looking, you follow the reaction, find the number of moles of one, and then use the mole ratio to predict the other. So next they say filter, dry, and weigh the precipitates. The equation for the reaction in step 1 is as shown below. Again, for step 1, you bubble excess sulfur dioxide into 100 centimeters cubed of potassium chloride. So we know this is going to be 100 centimeters cubed, and this is going to be the excess. And in the end, we will form the chloride, which is going to react to form with silver nitrate to form silver chloride, which will be the crystals we're going to obtain. However, because sulfur dioxide was excess, after the reaction has occurred, we will find a way of eliminating the sulfur dioxide through this step 2, where they boil the mixture, which is the solution, to get rid of the sulfur dioxide which was in excess. So here they say identify the main hazard in step 1, giving the safety precaution that will reduce the risk. This is sulfur dioxide, which is a gas that can react with water even in air to form a corrosive acid. So it's toxic, it's corrosive, you have to know that. If you're working with such toxic and corrosive gases, you have to use a fume cupboard. A mask will not be able to help you alone. You need to work in a fume cupboard in order for the fumes to be removed when they are sucked out of the lab. The next part says the reaction in step 2 produced that mass of course, the white precipitate is going to be silver chloride. Calculate the concentration of potassium chloride in the solution in mole per decimeter cubed found using method 1. Now from method 1, we know we have to find the molar masses of each. Silver chloride has a molar mass of 143.4. So since they told us this is the mass that was obtained, we begin by finding the number of moles of silver chloride. Number of moles of silver chloride will give you the mass, which we have seen it's here, divided by the molar mass, and it gives us those moles. If you use a calculator, you get the answer. And then to find the moles of silver chloride, since we have the moles of silver chloride basically, you need to know that the moles of silver chloride are going to equal to the moles of silver due to this reaction. 1 mole of silver produces 1 mole of silver chloride, and therefore 1 mole of chloride produces 1 mole of silver chloride. So using a 1-to-1 mole ratio, it means the moles are similar. And since, again, let me go back up here, you see there is going to be 1 mole of chloride producing 1 mole of chloride, so it means the number of moles of chloride are also going to be the same. So moles of chloride are equal to moles of chloride. So if we know that the moles are similar, it means we can use that to find the concentration. So concentration will be number of moles divided by volume, which is the moles we have there. And the volume given to us was 100 centimeters cubed, but we need to convert this volume into decimeters cubed. You divide by 1,000. Divide by the volume in centimeters cubed by 1,000 to convert it to decimeters cubed, so that you can be able to find the answer in moles per decimeter cube. So if I round off, I got 0.0300 mole per decimeter cube. Let's go to the next part. A student who used method 1 obtained the value that was significantly larger than the actual concentration of the solution. Okay, so they say explain one possible source of experimental error which might lead to this result. The only issue is, in the experimental steps they told us, the student did not wash. Remember, they obtained silver chloride precipitates. However, they just filtered. They did not wash because you wash off some of the impurities that might be left back. In this situation, you know, there were so many components within the product solution. So filtering the precipitates alone does not help. You have to wash them. If you do not wash, you're gonna weigh a mass that is gonna be higher than it should be, and this is gonna affect your calculations. you'll end up getting more moles than you thought than really are there, because you have measured the impurity as well, and it's going to affect the whole process basically. So here what they had to do is they added silver nitrate. Remember, silver nitrate is going to be soluble. The silver nitrate that was added was still in solution. Although it's soluble, some of the ions are going to stick onto this, and if they're not washed off, they are going to cause a higher mass, and which could lead to a wrong calculation. So let's see titration 2, method 2. Step 1, mix a sample of potassium chloride solution with acidified solution containing iron 2 sulfate. Okay, then remove the chloride ion produced in step 1. Then determine the concentration of the excess ion by titrating the whole of the solution with a standard solution of potassium manganate. If you remember the titrations you looked at in your textbooks, potassium manganate as well as iron do react. You talked about redox titrations. This is one of them. So here we see the equation for the reaction in step 1 is as shown below. Again, step 1, remember you're reacting potassium chloride 5 as well as iron 2 to produce iron 3 and then chloride. So here they say give the color change that you would observe. The color change is going to be green to yellow. And how can we know? Because here we're going to have iron 3. Iron 3 is going to cause that color, and iron 2 is going to cause this color. That is going to be colorless. The chloride is colorless and water is colorless. So the colors we're going to see are going to be due to the ions. So iron 2, which is kind of green, and iron 3, which is yellow-brown. So you see a transition from green to yellow. Next, they say describe how to carry out a titration in step 3. You should identify suitable apparatus and any additional chemicals required. Here, we need to revisit step 3, read through, and then determine how we can be able to describe the steps in that titration. So step 3 said, determine the concentration of excess iron 2 ions by titrating the whole solution with a standard solution of potassium manganate 7. The key thing is usually we put the standard solution into a burette, and then the solution, in this case iron 2, should be put in the conical flask. So let's begin. So you need to, of course, in the conical flask, if I can draw like that, whatever we're going to put in the conical flask and whatever we're going to put into the burette, yeah, my art skills are worse, so please bear with me. Okay, whatever we're going to put in here, this sample we put in this burette should be the standard solution, whose concentration is accurately known. Standard solution, and in this case is the manganate 7. And here what we're going to put in the conical flask is going to be the iron, basically iron 2 plus leading to iron 3. So that is going to be how we work out here. So let's see, we will transfer the solution of known concentration of potassium manganate into a burette. When you're transferring into a burette, you need a funnel so that things do not spill over, and to avoid bubbles sticking to the sides of the burette, basically. The funnel helps you to make a clean transfer of solution, and it makes the appearance of bubbles to be minimized. Next, you will transfer a known volume. Remember, this volume we put in here has to be known volume. Okay, a known volume of the mixture of potassium chloride as well as iron sulfate into the conical flask using a pipette. Usually we transfer 25 centimeters cube. And then the next step is going to be you're going to release the standard solution, which is potassium manganate, into the conical flask while swirling. To swirl, it's like to mix properly in order to prevent, to have the reaction occur homogeneously. And so in this case, the first titration is going to be the rough titer. So for the rough titer, you're going to pour as you release the standard solution, which is potassium manganate, into the conical flask as you swirl, and then determine the end point using the rough titer. And then the next, we're going to carry out other titrations. So carry out a titration using the reference from the rough titer, and drop-wise add potassium manganate until the end point is reached. After that, we will make sure we carry out more titrations to get concordant results. So record the volume of potassium manganate used when the contents in the conical flask form a permanent pale pink. This is the color at the end of the titration. And once you have got that volume, then repeat the titration until concordant results are obtained. Concordant results are results that are within plus or minus 0.2 centimeters cubed of each other. Then you can know that your titration was successful. In method 2, 50 centimeters cubed of potassium chloride 5 was mixed with 150 centimeters cubed of 0.0750 mole per decimeter cubed of iron 2 sulfate. The iron 2 sulfate was in excess, so the whole of this solution required 9.25 centimeters cubed of 0.05 mole per decimeter cubed of potassium manganate 7 to completely react. So we were given the two equations for this reaction, and we are asked to calculate the concentration in mole per decimeter cube of potassium chlorate 5 solution. So we will begin with the information we know. We know we were given the information about iron. Let me use a highlighter here. We were given the information about iron, as you see, iron 2 plus. However, it was in excess, so we cannot use these. Even if we can use the concentration and volume to calculate the number of moles, those moles are going to be in excess, so they are not representative. However, we are given the information of manganate 7, so it is better to use the information of manganate 7 because the manganate 7 reacted with the leftover iron 2. So if we use manganate 7, get the number of moles of iron 2, we can work backwards to subtract the moles that were left, which is the excess iron 2, minus the number of moles of iron 2 that were there initially, to be able to know the moles of iron 2 that reacted with the sample in the first equation. So let's see. The initial moles of iron 2, we are using these ones here. These are the initial moles. So we will say it's going to be number of moles is concentration times volume. We have the concentration, and we were given the volume as 150 centimeters cubed. However, we have to convert the volume into decimeters cubed. So we divide 150 by 1,000 here, 150 by 1,000, to be able to convert volume into decimeters cubed. And this comes out as the number of moles. So this is the initial number of moles of iron 2 plus. However, we need to also find the number of moles of manganate. Remember, the number of moles of manganate are going to give us the number of moles of iron 2 that was left at the end of the reaction. So this is also going to be concentration times volume. The concentration is 0.05. The volume is 9.25. When we divide that by 1,000, we get the volume in decimeters cubed. Multiplying that and that, we get the number of moles, which is that. So these are the moles of manganate basically. However, we're going to use this with a mole ratio to find the number of moles of iron 2 that was remaining at the end of reaction 1. So the moles of iron 2 left was 5 times the moles of the manganate that was there, or the manganate that was provided. The key thing is to see here, if you look at this, the mole ratio is 1 to 5. So if you have the number of moles of this, to find the number of moles of that, just multiply them by 5. So it gives us this. It gives us that one here. So this one here. So which is that. And then lastly, if you want to find the number of moles of iron 2 that reacted, we're going to subtract the moles that were there initially, initial moles, minus the moles that were left behind, which is this. And therefore, that gives us 8.9375 times 10 power negative 3. Now, these are the number of moles of iron that should have reacted in here. So again, this question, remember, asked us to find the concentration of potassium chloride. Since we now know the iron 2 that reacted in here, we're going to use the mole ratio, which is 6 to 1, iron 2 to chloride. Here. This is 6, here 1, and that is going to be 6. So if we have the number of moles of this one here, we can divide it by 6 to find the number of moles of chloride. So here, that's why we have the number of moles from above, divide them by 6, we get the number of moles of chloride. And then finally, we can find the concentration, which is going to be number of moles divided by volume. So again, volume is 50 centimeters cubed. Divide that by 1,000 to convert it to decimeters cubed. And that comes out as our final answer, 2.97917 times 10 power negative 2 mole per decimeter cubed. Explain the changes, if any, to the values stated in calculated in F if the chloride ions were not removed before the reaction in step 3 of method 2. So if the chloride ions were not removed, they would have reacted with, of course, with the manganate, and manganate would also have reacted with iron 2. So it means the manganate, which is in here, into the burette, would have reacted with two things that are already in the conical flask. Remember, we would have iron 2 as well as chloride. These two would both react, leading to a more volume of manganate being required from the burette. So we would overestimate the volume used up, and therefore give us a wrong estimate of the number of moles. So here, in my conclusion, I say the potassium manganate added afterwards would have reacted with the chloride ions in the oxidation reaction to produce chlorine, This would lead to an increase in the volume of potassium magnate, of course, released from the burette, and a decrease in the concentration of the chlorate ions calculated. This brings us to the end of question 2. Let's go to question 3. Azo such as organol brown can be made from benzene using the reaction scheme shown. Due to the toxicity of benzene, the first step is never carried out in a school lab. So here we have benzene, which is converted into nitrobenzene. This one here is a nitration reaction. Nitration using concentrated nitric acid and concentrated, of course, sulfuric acid. So here we go to the next step. So they do reduction. Reduction here we use tin with concentrated HCl. And then finally we go to diazotization, of course, formation of the diazonium ion. Here we need either you can use sodium nitrite with a dilute HCl, or you can use nitrous acid. However, of course, when you're writing, you can say nitrous acid, but in real life, you cannot use nitrous acid because this step here, the nitrous acid is prepared in situ during the reaction. So as the reaction is going on in the conical flask, they will put sodium nitrite and hydrochloric acid so that nitrous acid is produced within the conical flask during the reaction. And finally, we see the making of the azo dye, where something that has an alcohol and then the benzene diazonium salt, of course, phenol and a benzene or a benzene ring that has an OH is reacted with a diazonium salt to form an azo dye. So this is the azo dye. So that is the breakdown of the reactions, of course, that occur here. So let's see, they say in the preparation of nitrobenzene, benzene is added slowly to a mixture of concentrated nitric and sulfuric acid. The temperature, so the mixture is warmed at 55 degrees under reflux for 45 minutes. The reaction mixture is stirred continuously. State why a reflux condenser is needed when the mixture is warmed. Now remember, here we have nitric acid and we have concentrated sulfuric acid. However, we have benzene as well. Now benzene is purely a hydrocarbon, but these others are aqueous. A hydrocarbon and aqueous compounds cannot mix well, so we need to use a reflux condenser to allow this time in order to interact for the reaction to go to completion. And another thing, benzene is actually volatile. So the reflux condenser will cool down the benzene as it's trying to evaporate so that you can return back into the boiling flask in order for the reaction to be carried out to completion. So the refluxing condenser ensures that volatile benzene does not escape from the reaction mixture. That is the perfect answer for this question. I will go to the next part. Of course, here they say draw a diagram of the apparatus used to warm under reflux in this experiment. Now, when you're drawing a reflux condenser, you have to put the condenser vertically. It has to be straight vertical. Water in should be at the bottom and water out should be at the top. This part here should be open. That end should never be closed, because if it's closed, then pressure is going to build up in here, which we are not interested in happening. So we have to make sure it's open. And again, here you can see sometimes you put antibumping granules. It's okay. The reaction mixture has to be down here. And please remember, you can use a special lab boiling flask, or you can use a pear-shaped flask, but you cannot use a conical flask or other apparatus that are not used for heating. Here I put a heating source, example electric heater, because most of the time you're trying to heat things that are easily flammable, so an electric heater is going to be safer. Usually when they are awarding marks, they award the condenser being vertical as well as water in, water out. Sometimes water in, water out is given a mark. The condenser being vertical and open is given a mark. Then the flask as well as the heating source could be given a mark. So this is usually a 3-mark question. I'll go to the next part. Suggest why the reaction mixture is stirred continuously. We stir continuously, of course, because of the immiscibility. Remember, these acids here are aqueous, and we would say maybe they are ionic. They're ionic in nature, while the benzene is going to be a hydrocarbon, which is basically not going to interact with ionic compounds. So we continuously mix them to allow the hydrocarbon benzene to make interaction with the aqueous layer in order for a reaction to occur between them so that products can be formed. So again, together, two maths I say, benzene and the acids are immiscible in each other. Continuous stirring prevents formation of the separate layers to ensure the reactants come into contact to enable the reaction to proceed. Now, in your answer, you do not have to write exactly like I did, but you have to include the keywords. Keywords we are looking for is the idea that benzene and the acids are immiscible, and therefore they will form separate layers, and the idea that when you mix them, the separate layers are broken, and therefore they do interact in order for the products to be formed. In your own words, to write it, you include the key details. Next part. The excess acid is removed from the reaction mixture. Remember the excess acid, we're talking about nitric acid as well as sulfuric acid. So they said the layer containing nitrobenzene is separated and dried before being purified by distillation. Identify the suitable drying agent. Because here they have said it is as dried. Something to be dried, it means these are now, it's going to be maybe a liquid that we have to extract out water. Extract out water. And since we know nitrobenzene is a liquid, how do you dry an organic liquid? You use a drying agent. And the drying agent has to be anhydrous. Every time you're writing an answer, please include the word anhydrous on every drying agent you use. Now, you can use anhydrous sodium sulfate, anhydrous magnesium sulfate, anhydrous sodium sulfate, magnesium sulfate, as well as anhydrous calcium sulfate in this case, or calcium chloride. Next, nitrobenzene is then reduced by phenylamine. The phenylamine reacts with nitrous acid at a temperature of course, 0 to 10 to form a diazonium compound. Nitrous acid is formed in the reaction. This is what I told you. We form nitrous acid in situ by using sodium nitrite and hydrochloric acid. State why nitrous acid is generated in the reaction mixture instead of being obtained from the chemical supplier. Guys, if you buy nitrous acid from the manufacturer, this acid easily breaks down, producing byproducts, and producing products which it easily degrades or breaks down or decomposes. And when it does, it means you're not going to have it available to act as a reagent in the reaction you're interested in. So I say nitrous acid is unstable. This is very important, and therefore it's going to decompose before it's used. So we use sodium nitrite and HCl so that these will interact to give us the main thing we are looking for, which is nitrous acid, which is a reagent, of course, plus other things, but this is the reagent we're interested in during the formation of the diazonium salt or diazonium compound. So explain why the temperature of the reaction between phenylamine and nitrous acid must neither be lower than 0 or higher than 10. If it's lower than 0, then it means that the kinetic energy is going to be less. Kinetic energy is going to be less. Energy is going to be less. Then the substances are not going to collide with each other, or the reactants are not going to collide with each other with the right amount of energy for a successful collision to occur in order for a reaction to occur. So here we will have very low activation, very low kinetic energy in order to reach the activation energy required for the reaction to proceed. So the rate of reaction will be lower if the temperature is below 0. If the temperature is higher than 10, there is a chance that the product, which is the diazonium chloride, is going to be hydrolyzed, because remember the products will be diazonium chloride as well as water. So the water will react with the diazonium chloride, converting it to, as you can see here, this is what I wrote here. So the first one is when we react at a temperature between 0 to 10, we will get the product we're interested in. This is the diazonium salt as well as the water. However, if the temperature goes above 10, then these two are going to react with each other. Hydrolysis will occur, which will lead to the formation of phenol as well as nitrogen and water. That is what we are trying to prevent, reaction above 10 degrees. So this will form an intermediate, which is going to decompose to form phenol and nitrogen as well as water. So I said below 0 degrees, the reaction would be too slow, of course. This is just a 2-mark question. Even if you do not explain the whole idea of lower kinetic energy, fewer chances of collisions, you don't have to say that. just say below 0, the rate of reaction is going to be too slow. Above 10, the diazonium chloride will be hydrolyzed to form phenol as well as nitrogen gas. Next, so here we see reaction of a diazonium compound with alkaline solution of naphthalene 1-or produces the solid as a dye organobrown. The solid is purified by recrystallization. Again, you guys be very careful about recrystallization. You better understand it for any Unit 6 chemistry paper you're going for. Recrystallization is usually there. So procedure, step 1. The impure organobrown is dissolved in a minimum volume of hard solvent. Remember, they've said minimum volume of hard solvent. This ensures that we do not use too much solvent in order for the crystals to be easily formed when we are trying to cool down. Then step 2, the solution is filtered when hot. The reason as to why we filter when hot is to remove any insoluble impurities. Any impurities that would not be soluble in the solvent we have chosen will not be dissolved when the solvent is actually hot. It means it allows us to filter them when the solution is too hot, to be able to separate them from the crystals when they cool. So basically here they say the solution is filtered hot through a preheated funnel. Using a preheated funnel prevents clogging of the funnel when you filter. So 3 says the solution is cooled and filtered using a Bachner funnel. This is done to remove the soluble impurities. Then the solid is rinsed with a small amount. Again, here there is a small amount of ice cold solvent. You want to use small amounts so that you prevent the sample, the crystals you're trying to get, from dissolving back into the solvent. And this has to be cold to minimize the chance of dissolving, of course, the solvent, the crystals into the solvent. Step 5, the solid is dried in a desiccator. Of course, this is okay. Step 1, they say, state why a minimum volume of hard solvent is used in step 1. To ensure that the solution is made saturated enough. Remember, you have your crystals. You put in some solvent. You do not want to use too much of a solvent. The reason as to why we put in hard solvent is we want to make sure the crystals of interest do dissolve. However, anything that does not dissolve, we're going to filter it out because it's going to be an impurity. So we don't need to use too much solvent, because when we use too much solvent, then we have to evaporate it off during the process of cooling down, which could be very hard for us to do. So if too much solvent is used, it will be hard to recrystallize or the organobrown from the solution. That is perfect. Then the next part says, explain why a preheated funnel is used. You can see I underlined everything that is important because I knew questions like that usually come up. We use a preheated funnel to prevent the blockage or the sample from clogging the funnel when the filtration is occurring. If the funnel is cold, you're filtering the sample is going to cool down as it's passing through the funnel, and crystals might be able to form and clog the funnel, which we are not interested in occurring. So this prevents crystallization of the dye in the funnel, which might cause blockage and loss of the sample. So next part says, give a reason for each of the following filtrations in step 2 and step 3. Step 2, we filter when hot to remove insoluble impurities, and we filter when we cool down, of course, using a Bachner funnel to remove the soluble impurities. Next says, give a possible reason why it is preferred to dry the solid in a desiccator rather than in an oven in step 5. We use a desiccator because, of course, these are crystals. If we use an oven could cause thermal decomposition of the crystals we've produced. Remember, the temperature within the oven could be a little bit higher, causing the crystals to decompose, which we do not want. So using a desiccator that does not require heat, just sucks out the water. That is a better choice we can use. Lastly, the melting temperature of the crystallized organobrown is measured to check the purity. State what you would observe if the sample was pure. If the sample was pure, a sharp melting point is going to be observed, and so that's it basically. If it was impure, of course, you see it will melt over a range of temperature, and again, the melting temperature will be lower than the data booklet value. This brings us to the end of this paper. Thank you for being with us. Please remember to subscribe and see you in our next video. Thank you.